we're going to take a look at Gauss's law, which deals with inverse square fields. I want to just point out that your book deals with this as example 3 in your text in this section. There they're dealing specifically with F being an electric field. That's one example of an inverse square field. I'm going to work through Gauss's law just for a generic inverse square field, but I'm aware that many of you, particularly those of you taking physics classes where you're studying electricity and magnetism, are going to be most familiar with it in the context of an electric field. Okay, so that's where this is done in the book. They do refer to it as Gauss's law, but it's not sort of highlighted as a separate section. So look for example 3. Okay. All right, so I'm just going to remind you that I'm letting R, which is just x, y, z, be my position vector. And for any inverse square field, I can describe it then as some constant divided by the magnitude of R cubed times R. Remember, 2 of those factors are from the fact that the magnitude of my force is going to be inversely proportional to the distance that I am from the origin, which is just the magnitude of R. The third factor comes from the fact that what I'm really scaling here is R hat, the unit vector in the direction of R, which would be R divided by its magnitude. Depending on whether C is a positive or a negative constant, an inverse square field will always be acting either straight away from the origin or directly towards the origin. Okay, so Gauss's law is kind of neat because it says if S is any closed surface that encloses the origin. Now, a closed surface simply means that it's the boundary of a finite solid. So it's not open-ended. It wouldn't be something like this paraboloid, which is open-ended, so that we've discussed the fact that if I filled it with water and flipped it upside down, the water would pour out. Now, if I capped it with a disk on the top, then I would have a piecewise smooth closed surface because it would be the boundary of a finite solid. So saying closed surface just says it's the boundary of a finite solid. And if I want to be able to integrate an inverse square field over a surface, the origin either has to be, closed surface, the origin either has to be strictly inside or strictly outside of that surface. It can't be on the surface because the inverse square field is not defined at the origin. Remember, its domain would be all of 3 space minus the origin because that puts a 0 in the denominator, which we know we can't have. So if my surface included the origin, my integrand would be undefined at a point on the surface and the whole thing would be nonsense. So I pretty much have 2 possibilities if I'm working with a surface and I'm working with an inverse square field. I could have something like so, where the origin is inside of the surface, or I could have something like so. Here's the origin, and my surface is over here. Okay. Now my surface doesn't have to be a sphere. That's just a convenient surface to draw. Okay. Convenient closed surface to draw. Now, if the origin is completely outside of the surface, then evaluating the double integral over S of f dotted with n ds is ridiculously easy, because then the divergence theorem applies, and I can say this is just the triple integral over E, where E would be the finite solid contained on the inside of the divergence of f dv. But we proved back in the section on divergence and curl that both the divergence and curl of an inverse square field are 0. So this would just be the triple integral over E of 0 dv. And of course, if I integrate 0, I'm going to get 0. That's ridiculously easy. Why can't I do that here? Well, because if f isn't defined at the origin, then neither is the divergence of f. That's not going to be defined at the origin, so I couldn't integrate over the enclosed region because my integrand, divergence of f, would be undefined at some point. Okay. So I can't use the divergence theorem directly if I've got something like this, where I've got a closed surface that encloses the origin. Okay. And that's simply because the divergence isn't defined at that one point on the enclosed solid. Okay. But Gauss's theorem says that no matter what the surface is, this is kind of crazy. So my surface could be a sphere. It could be a sphere of radius 1. It could be a sphere of radius 22 million. My surface could be a piecewise smooth rectangular box. My surface could be a completely blobular region as long as it's piecewise smooth and it's a closed surface that encloses the origin. No matter what it is, the flux across that surface is going to always be the same. It's always going to be 4 pi times c, where c is the constant that shows up in the inverse square field. That's kind of amazing, okay? That it's going to be the same regardless of what the surface is, okay? And we're actually going to prove that using the divergence theorem. But like I said, I can't use the divergence theorem directly because right now the divergence is undefined at part of the enclosed region. So we're going to have to modify things a little bit in order to actually prove this. So here's what we're going to do. I'm going to just draw myself a bigger picture here. Okay. So the origin, that's my problem point. I'm going to suppose that I've got S, some surface. I'm going to just draw it as a big sphere, but it doesn't necessarily have to be a sphere. Like I said, it could be a rectangular box. It could be a blobular surface. Doesn't matter what its shape is. This one's just relatively easy to draw. Okay. Now, I have this problem in that I can't apply the divergence theorem because I've got the origin there. So what I'm going to do is I'm going to draw a very small sphere. This one I am going to choose to be a sphere of radius a, centered at the origin, that encloses that origin, and I'm going to take that region out. Okay. So I'm going to say S sub a is the surface of a sphere of radius a, centered at the origin. And very important, it's completely contained inside of S. Okay, excellent. Now, it is possible to do that. A theorem from some more advanced math tells me that if I have a situation like this, there's going to be some point on S that's the closest to the origin. I'm going to measure the distance of that closest point to the origin, and I'm just going to make sure that A, the radius of this inside sphere, is smaller than that distance. Okay. And then I'm going to define E to be the region between S and S sub a. So that's going to be a solid region. You can sort of imagine it as it's the candy part of a Tootsie Pop. So this is very sad to think of, but imagine you had a Tootsie Pop and some very evil, wicked, horrid, mean person removed the Tootsie. Then you would just have the hard candy shell. That's sort of what E looks like, at least if S is roughly a sphere. Of course, you could have a distorted, deformed candy part of a Tootsie Pop if S was not round, but that's perfectly fine. It's a Tootsie Pop with the Tootsie removed. Okay. Now, I know that now over E, the triple integral over E of the divergence of f dv, that's now well defined because the origin, which was the point where the divergence of f was undefined, that was part of the Tootsie. We removed it from the Tootsie Pop. So this is just the triple integral over E of 0 dv. That's just 0. Okay. So over this region, I can apply things. So now I just have to say, could I use the divergence theorem to say this is the same as calculating the flux across the boundary of E? And the answer is yes, we can, but the boundary of E is a little bit more complicated than anything we've seen before. Because the boundary of E, we've actually got an outer boundary, which is S, and an inner boundary, which is S sub a. So we've got to deal somehow with those two boundary parts. So we've been going for a little while here. I'm going to stop this video here, but what we're going to do is figure out how to describe the boundary of E so that we're able to then calculate the flux across the boundary of E. And I know it's got to be 0 because the divergence over that enclosed region is 0. So when I integrate divergence over the enclosed region, I get 0.